Hello everyone, I'm Max from USC, and I'm very happy here to present our recent work about Megalodon, which is an efficient architecture for pre-training with long context. Okay, so this is joint work with my co-authors from Meta, CMU, USSD, and Shanghai Jiao Tong University. So I think transformer, once it has been proposed 7 years ago, transformer has been applied almost everywhere in machine learning and unlocked a bunch of like applications, including like text, speech, biomedical, and also like images. But we know like transformer is still not perfect. And one challenge for transformer is to handle like long context. And before we dive into the details of long context modeling, we want to first ask like why long context is important in today's machine learning. So I think the first motivation is that we believe long context is like usually like equals to like higher level intelligence and also better performance, and also it is like a good test bed to measure like the capability of an architecture. So for example, here is the comparison between ISTM and transformer. So we see that if our context length is short, it's within like 100 tokens, then transformer and STM behave similar with each other. So their performance is not big different. But if we scale the context length to 1,000 tokens, then we see that transformer starts to perform much better than STM. So this results just show us like long context is a good setting to test the model's capability. And also we know like long context enable us to build more advanced applications. For example, if we want to build like book level translation or summarization system, or if we want to build like a personalized AI assistant.
Sorry, can you point with your mouse a little bit, turn on the laser pointer, because it's hard for us to follow what you're talking about. Thanks.
Okay, got it. So once we want to build some more advanced applications like personalized AI assistant, or if we want to use, if we want to model like long videos or in some real world setting, then we need the model to be able to handle like long context. And but we know that long context is hard for transformer. I think the first reason is obvious, the complexity. And in transformer, the computation is quadratic with respect to the length of the input. And here h is the heads, the number of heads of attention. And in practice, h is also like a big number, so which makes the complexity even worse. And here is empirical comparison between the flops in attention and non-attention components in a transformer architecture. So we see that if our context length is short, it's shorter than 8,000 tokens, then attention, the computation cost in the attention part is not the bottleneck. But if we scale up the sequence length to more than like 1 million tokens, then almost all the computation happens in the attention parts. So that's why transformer is expensive for long context modeling. And not only the computation, the amount of computation, but also the way we distributed our devices is hard to compute the full attention. So this is because for full attention, we need to compute like pairwise pairwise inner product of the key and values, query and keys. And if we want to parallel our computing, then for each device or for each GPU, it needs to collect all the keys and queries from other GPUs, which just trigger a significant amount of communication. So which makes our parallel computing like more expensive. And even with the most advanced like real attention mechanism, we still need like the full attention computation is still slow. So in practice, if we want to compute a full attention with 1 million tokens, then it still spans about around like 10 minutes to compute like one forward and one backward pass. So that's that is unacceptable in practice. And the second reason why long context is hard for transformer is that transformer is hard it's hard for length extension or generalization. So here is the comparison between transformer and Mamba model in the length extension experiments. So we see that for both of the two models, they are pre-trained with 2,000 tokens. But once we apply the pre-trained model to longer context, then we see that Mamba model works well. The loss is stable, at least within some range of the tokens, but transformer model is just the loss just explode immediately after we have like a longer context than pre-training. And this is because the problem is because that for transformer, the only positional information is from the positional embeddings. And if for some positional embeddings which has not been trained during training, then the model may just be unstable on this case. So this makes the transformer like even harder to be applied in practice, because in practice sometimes we need to apply a pre-trained model to longer context. And so with the two major problems of transformer on long context modeling, so we want to ask a quick question. So if we can split the full attention into chunks, and we only compute attention within each chunk, then we can essentially resolve the two big problems. So first, because we only compute attention within each chunk, so the complexity just becomes linear and it is efficient. And also because we only have positional embeddings within each chunk and the chunk size is fixed, then we do not need to worry about like length extension, because there will never be positional embedding, unseen positional embedding. So this is the two big props of chunk-wise attention. But the cons is also obvious. That is, if we just split the attention into chunks, then we just lose the longer context or longer dependencies across different chunks. So, if we can, so the basic idea behind our first version of mega architecture is that if we can build an efficient component which serves as a connector for the chunk-wise attention, so that we can reconnect the boundaries between the chunk-wise attention, then we can recover the lost long dependencies in chunk-wise attention, but still keep the advantage of efficiency of the chunk-wise attention. So that's the basic motivation of the first version of our mega architecture. And in the mega architecture, to achieve this goal, we propose like three components. The first one is called like the EMA layer, EMA component. and which just utilize the decaying exponential moving average mechanism. And the second is the single head like gated attention mechanism, which we aim to reduce the number of heads in multi-head attention. And then we just combine them together to achieve like long context modeling and also good performance. So let's first see what is the EMA component in Mega. And so we know like EMA is a very classical method, and it has been widely applied to different areas. And I think one of the most important application of EMA is for signal smoothing or signal processing. So we can see that if our signal is noisy, and it is hard for us to directly see some like clear trends behind the noisy signal. And if we apply EMA, we can significantly smooth the signal and get a more clear distribution of how the signal look like. And this is just the basic idea behind EMA. So basically, EMA is just like weighted sum of the signal. So suppose if we have our input, which is a one-dimensional sequence from x1 to xn, and then at each step t, we just use a decay factor alpha to sum over the current input xt and the previous hidden state like t minus 1. So, and our decaying factor is in the range from 0 to 1. So this is just a weighted sum. And this is the original form of EMA. And we see that here is the figure to illustrate the mechanism. So we can see that at time step t, the hidden state yt it is just the weighted sum of all the previous input from the other previous input till the time step t. And at different time steps, the input has different weights, and the weights are decaying exponentially over time. And in practice, we found like the constraint of the weights in EMA is too restricted. So here, EMA requires the weights to sum equals to 1. But in practice, we can introduce another damping factor, delta, to relax this constraint. So for example, here we just add a delta here. Delta is also in the range from 0 to 1. And by adding this delta, we can relax the constraint. Now the two weights are not necessarily equals to 1, sum equal to 1. So we just improve the EMA's capability. And in our Mega model, both the alpha and delta are just some learning parameters similar to the parameters in transformer. And the next question is like, how could we efficiently compute the output of an EMA layer? So we see that in the formula, EMA is just a recurrent architecture. So it seems like we need to compute the output of YT one by one. So we need to compute the output of YT minus 1 first, and then we compute the output YT based on YT minus 1. But in fact, there is advantage of EMA because we can compute it in an efficient way. This is because our decaying factor alpha and delta, these two factors are independent with our input. So in this way, we can formulate EMA as a long convolutional format so that we can compute EMA with the fast Fourier transform. And this can be compute parallel on GPU devices. So here I want to say that EMA is like
question in the audience.
Sorry, question. Are alpha and delta scalars or vectors?
Vectors. So it's like for each input dimension, for each input dimension x xt, it is number, but because our input has multiple dimensions, so for each dimension it has different alpha.
Thank you.
Yeah, and here I want to say that EMA can be regarded as simplified version of state space models. And for example, if we compare EMA with Mamba, the only difference is that Mamba, in Mamba, the alpha and delta, these parameters are input dependent, and in EMA, they are input independent. So in theory, one layer of Mamba is more powerful than one layer of EMA, but the cost is that Mamba cannot be, so to compute Mamba, we cannot apply the fast Fourier transform. So in practice, Mamba is slower. One layer of Mamba is slower than one layer of EMA. So we just, sacrifice a little bit of the complexity, but we
Max,
achieve
may
like,
I ask one quick question?
Yes.
So this is element-wise vector product, right? In this?
yes, element-wise, yes.
Okay, thanks. Yeah.
Yeah, so as I said, like we just for EMA we just sacrifice a little bit like capacity, but we achieve like more efficiency. And so here is a summary of the EMA layer. So we can see that in EMA favors recent and local context because it uses the exponential decaying factor. And in principle, it can peak and unbounded context history, and it's efficient to compute, but it's less powerful than Mamba or transformer layer. And the second component of the Mega architecture is what we call like single head gated attention. And the motivation behind this gated attention mechanism is to reduce the number of heads in multi-head attention. So here is the attention formula, the standard attention formula. So we just compute the attention matrix, and then we multiply the value tensor to get the final output. But in practice, we know that we need to use like multi-head attention to compute O, and the number of heads is not it's not a small number. Usually we need to set the number of heads to 32 or even 64. But the question is like how much benefit we can get from the multi-head attention. And obviously multi-head attention is better in terms of performance than single-head attention. But our theorem tells us that this kind of benefit is not significant. And also we can replace this benefit just by adding a single gate on top of the attention output. So here, suppose we have a gate function gamma, which is for example, we can use MLP to model the gate function from the input X. And then once we have the single head attention output O, we just directly apply the gate on top of O. Then we can get the output of single head gated attention. And our theorem tells us that if gamma is a universal approximator, then the single head gated attention is as powerful as any multi-head attention. Yes, question.
Yeah, I thought gating, I thought multi-head reduces the cost because all the matrix dimensions go down because you're sort of, instead of dealing with D-dimensional matrices, you're dealing with D over H dimension.
Oh, but that's one head. But in practice, we need to do H heads of what you said. So yeah. I mean, the whole computational resource, whole computation is the same, and the memory cost is H times.
But doesn't it sort of block sparsify the matrices because they are become D times D over H or whatever?
Yeah. So for each head, we have D over H, right?
Yeah.
But we have H heads, so we just put H back when we compute the whole cost.
Okay.
Yeah. So and also for memory, because we need to compute H times of this matrix, which shape is n times n. So the memory cost is H times larger than single head.
Okay, got that. Yeah.
Yeah. And so our theory tells us that the benefit of multi-head attention can be covered by just introducing a single head, a single gate. And as I said, like this is a theory. This is in theory. In practice, we still found like we need multi-head gated attention, but we can significantly reduce the number of heads. And I will come back to these details later in the experiment part. But in practice, we can reduce the number of heads by eight times in our experiments. And then we just need to combine like the EMA layer with the single head gated attention to get our mega architecture. So what we want to say here is that the way we combine these two components is not just stack them one by one. We have like some mechanisms to better combine them. For example, we just use the EMA layer to compute the Q and K, and the value is still from the original input, and also we have some gate here to combine them. So after we get the our mega architecture, we can so here is the summary. So we can see that with the mega architecture, because we have the EMA layer and we have the chunk attention, and the EMA layer just serves as the reconnector of the chunk boundaries. So in practice, in principle, we can see the model is able to see the whole context. And here are some like preliminary experiments we conduct for the mega architecture. So we just conduct experiments on long-range arena and language modeling with Wiki8 and Wikitext 103, and also some machine translation benchmarks, and also image classification on ImageNet, and also raw speech classification on speech comments. And here are the results. So XSM is short for transformer. And we see that on top of on all the benchmarks, Mega achieves like much better performance than transformer and S4. The only exception is on raw speech classification, where Mega is slightly worse than S4, but on other benchmarks, Mega is much better. And so here is our first version of architecture named Mega, but even it achieves like promising performance, we still see some limitations of this architecture. And the first limitation is that we still see like our like EMA is not strong enough. So here is the evidence. So we see that if we still use full attention in the mega architecture, it means like we do not use chunk-wise attention. We use full attention with the EMA layer. We see that we achieve like much better performance than the version of mega with chunk-wise attention. So this means like the chunk-wise attention with EMA is still worse than the full attention with EMA. It indicates that the chunk-wise attention is still the our EMA layer is still not strong enough to fully recover the long distance dependencies. And the second like limitation of mega is that it is a problem not only for mega, but it's a problem for, I think, for almost all the architectures. So that is what we call like architectural divergences for different data modalities. So here is the so we see that even though in this figure we call this model transformer on different tasks, and we call this model like S4 on different tasks, but actually these models are not the same model, not the same architecture, because for different tasks there are still some architectural differences. For example, for text models, we usually use layer norm or RMS norm. For image data, we usually use like batch norm or group norm. And also for different tasks, sometimes we use pre-normalization, sometimes we use post-normalization. So it means like for different tasks, even though the whole architecture seems the same, but a lot of details are still different. But in practice, if we want to apply a single architecture to multi-modality tasks, of course, we hope that our architecture is unified. There is no any architectural differences between different data types. So this is our goal. So we want a unified architecture that works well across different model modalities. And yes.
Isn't a unified architecture by definition a slightly less efficient architecture for all of those modalities?
Sorry, what is the question?
Don't you risk becoming less efficient by trying to be more general?
Oh, yes, that's a good question. So the reason why, let's see this table, the reason why people use different variants of their architecture for different tasks, because like on different tasks, if we want to achieve the optimal performance, we need to tune this kind of architectural hyperparameters. And our goal is that we can develop a unified architecture that on different tasks, the unified architecture can achieve optimal or even or at least comparable performance, even we fine-tune the hyperparameters. This is our goal. We want to develop a unified architecture with the optimal performance, but without sacrificing the efficiency and other like properties.
I don't know enough about it, but wouldn't it almost by definition always be a compromise if you're doing that?
So you say like maybe it is impossible, or
I'm not. I don't use the word impossible. I'm just wondering. I'm just wondering if by going general, you're ending up compromising on the final performance or the final efficiency. Or you're likely to. It seems unlikely that the most general solution is also going to be the optimal solution.
Okay, got your point. So, but at least I will show you some like experiments results to show like at least in our experiments we show it is possible. So we just achieve like this kind of goal. Yeah.
Okay.
Yeah. And the last one of limitation of Mega is that our previous experiments are all in small scales, and there's no experiments for large scale pre-training with Mega. So based on these three limitations, we just developed our second version, which we named like Megalodon. So basically we have like three modifications for the architecture. So the first is that to improve the EMA complexity, we just extend the EMA layer to the complex field. And the second is that we to achieve like achieve a unified architecture, we propose a time-step normalization layer, which it works well. We show that it works well for almost all the data modality. And the third one is like for large-scale pre-training, we know like numerical stability is a very important property for an architecture. So in order to improve the stability of Mega, we propose like two modifications. One is called like normalized attention, and the second is called like pre-norm with two-hop residue. So let's first see the complex EMA. So the idea is that in order to improve the power of EMA, we just extend the alpha and the parameter of EMA to the complex field. And the way we did it is we just add like a polar form of the the parameter like theta, and then we just formulate the EMA as alpha with the with cosine theta plus like I times sin theta. So with the polar form, we just extend EMA to complex field. And why we want to do this is that in the matrix theory, we know that in the real number field, dense matrix is more powerful than diagonal matrix. But in the complex field, almost all matrix diagnoses over the complex plane. So it means that it indicates that in the complex field, diagonal matrix is much powerful than the diagonal matrix in the real number field. So in EMA, obviously our because we use like element-wise multiplication, so our matrix is diagonal. So in this way, if we extend it to the complex field, then we achieve like we should achieve better complexity. And also because we only extend the parameters of EMA to the complex field, so we won't like significantly increase the computational cost of EMA. So it is still fast. And yeah, and also.
So what is the parameter theta there?
Parameter theta is just a learnable parameter.
Okay.
Another learnable parameter, yeah.
Okay.
And sorry, it's also a vector?
So there is some details I did not show here. So for theta, it is not a vector. I mean, the how to say, we only use one scalar of theta, but we use we use some like mechanism to extend it to a vector. But inside this vector, there are some structures of theta. So the idea is that we want to make sure that our theta on different dimensions is able to spread uniformly across the circle. So if you want to see the details of how we design the theta, you can read our paper. Yeah. Yeah, and the second component we propose in our Megalodon architecture is called like time-step normalization. So we know normalization is first proposed in batch norm and in the computer vision area. And once it been proposed, one of the most important motivation is to reduce the internal covariance shift of the data. So that is why in the in batch or group normalization, usually the normalization is performed across the time step and also the batch step. The time step dimension, also the batch dimension. But we know that if we want to normalize across the batch dimension, it just incorporates some like technical difficulties during pre-training. So that's why people usually use group normalization in computer vision, which also normalize across the time step dimension or the sequence dimension. But in like NLP, we most commonly use normalization layer is layer normalization or RMS normalization, which only normalize over the feature dimension. And I think one reason is that in transformer or language model, we need to do autoregressive architecture. So if we use autoregressive architecture, then group normalization cannot be directly applied, because for group normalization, some future information will be leaked to the previous one. So, but in our model, we still want to keep the motivation of reducing the internal covariance shift across the time step time step dimension. So we just extend the group normalization to the autoregressive case, just like this one. So so that is at each time step, we compute the mean and variance across all the previous tokens. So this just for time-step normalization, we need to compute a cumulative mean and variance, because at each step, this mean and variance is different from other steps. And this is not very easy to implant in PyTorch. So that's why we provide efficient like CUDA kernel for this implementation. And the third one is for stability of the architecture. And the idea is just directly inspired by from the some normalization in attention, for example, the QK normalization. And we just design like normalization, normalized attention specific for our mega architecture, where we just add a normalization operator on top of the C representation, and we use the C representation to compute our Q and the key. And we see that after we apply this normalized attention mechanism, we do not need to use any the skill term in the attention matrix. We see like in the standard attention matrix mechanism, we need to compute the Q and the key and over like the square root of D. But here, because we have already done the normalization here, we do not need the square the skill term of square root of D. And the last one is for what we call like pre-norm with 2-hop residue. And this is just a small modification for the pre-normalization mechanism. So here is just a direct comparison between these two normalization mechanism. So here is the standard pre-normalization, where we just for each input X, we first do normalization and attention, and then we add the residue connection here, and then we use the updated output as the input of the FFN component. And for the FFN component, it's also like first do layer normalization and FFN, and then we add the new residue connection here. And if we unroll this formulation, we see that the final output of the pre-normalization block, it is the output of the FFN layer, the output of the attention layer, and also the output, also the original input X. So it is the sum of 3 components. But in practice, we found like the attention output, its gradient is unstable because it is the sum. It is the sum of over the whole value matrix. So we found like this component, this term, its gradient is unstable during training. And if our architecture is not large, it is not a big problem. But once we scale it up to 7 billion parameters with like 32 layers, then this becomes a problem, because we need to we need to stack like 32 layers. It means we have 32 this term. We need to repeat this term 32 times, and once the instability just accumulated, then sometimes it just triggers some like training, just make the training crashed. And our modification is very straightforward. We just reuse the original input X as the residue connection. So here it means like for attention, it is the same, but for the layer, for the FFN component, we did not update the residue connection. We still use X as the residue connection. And then our output is just the sum of 2 items, the FFN output and the original input X. So we know like, because we only modified the residue connection, so we did not change the complexity of the model. We just changed the way we compute the gradient. So it means like we won't sacrifice any model complexity, but we improve the model's stability. And so yeah, so since we have our once we have our Megalodon architecture, because we have the chunk-wise attention, so we can have a better parallel computing in our architecture, because we do not need to worry about the full attention across different devices. So in our architecture, we can minimize the communication cost by only pass the last hidden state of EMA to the next GPU. We do not need to pass any other key and values across different GPUs. So we just significantly reduce the communication cost. And here is the updated results on the previous benchmarks. And we see that our Megalodon architecture achieves like much better performance than the original Mega architecture. And also we see that the chunk-wise, the Megalodon with chunk-wise attention reduce the gap, like achieves the similar performance with Megalodon with the full attention mechanism. So it means like our complex EMA layer is much better than the original EMA layer. And also what is important is that in this table, for the Megalodon results, all the models use the same architecture. So there is no any architecture divergences for the model used for different tasks. So in this case, it means like at least we achieve like a unified architecture, which is able to achieve like comparable performance. So I want to say like for each benchmark, this unified architecture is the optimal one. Maybe if we highly fine-tune some architecture hyperparameters, we can achieve like slightly better performance on each different tasks. But at least our unified architecture achieves like acceptable performance compared with other architectures or compared with our own variants. And also we just apply Megalodon, we just scale up Megalodon to 7B parameter model sets and also pre-train it on 2 trillion tokens. And we just use exactly the same 2 trillion tokens used in Llama 2 model so that we can do a head-to-head comparison. And for other architecture hyperparameters, we just closely follow Llama 2. We use 32 blocks and model dimension 4096 and rotary position embedding. And the difference is that, as I said, like because we use gated attention, so we reduce the number of heads from 32 to 4 heads. So we just reduce 8 times of number of heads. And also for pre-training, we use 32,000 context lengths with the attention chunk size to 4K. And in Llama 2, they use 4K as the full attention. So this is another difference. And here is the performance. We see that for this figure, it is the training loss with the same number of training tokens. And we see for Megalodon, it achieves like much better training perplexity, especially at the end of training with 2 trillion tokens. Megalodon achieves like training loss is 1.7 and Llama 2 is 1.75. And for Llama with 30 billion parameters, the model is the final loss is 1.67. So our model with 7 billion parameters achieves like approaching the final performance of Llama model with 13 billion parameters. And also we evaluate our model on downstream tasks, and we see that on different downstream tasks, Megalodon is much better than the Llama 2 model with the same number of parameters. And also we compare the speed or efficiency of pre-training with transformer architecture. And we see that if we use if we use like 4,000 as the context length, then Megalodon is slightly slower than transformer. This is because for under 4,000 context lengths, the attention is not the bottleneck. And for Megalodon, we need to compute EMA and timestamp normalization, so it is slightly slower. But if we scale up the context length to 32,000, we see that Megalodon is around like 32% faster than the transformer architecture in Llama 2. And also here for fair comparison, for all the transformer architectures, we use the flash attention with version 2 of flash attention to accelerate the speed. So to make sure the comparison is fair. And also we just do some we did some evaluation on long text to show how well our architecture on long context modeling. And the first is to test the validation perplexity on long context. And we see that even we scale up our context length to 2 million tokens, our validation perplexity is still very stable. It still just keep decreasing. And also, we test some performance on long context QA tasks, and we see that Megalodon achieves almost the same performance with the Llama 2 long version, which is a long context version of Llama 2. It is a model from Llama 2, but continue pre-trained on longer context, selected longer context data with more continue pre-training. So we still achieve similar performance. And also we did some analysis of existing problem of Megalodon. So we still see that here is experiments to show the loss of our model on different different token positions. So we see that even though our final perplexity is good, but at each chunk boundary, for the tokens before or after the chunk boundary, we see that their loss is significantly larger than other tokens. So it indicates that there are still some bottlenecks between the attention chunk boundary, and because the information because we need the EMA layer to pass the information from the previous chunk to next chunk. So the EMA layer just needs to push a lot of information to the boundary of each attention. And then with this kind of much information on the boundary, then it just hurts the performance of the prediction of these tokens. So this is the bottleneck in our current architecture, and this is the major direction of our future research. Yeah. And okay, this is my talk, and we have released our code on GitHub. And if you're interested, you can see our implementation. Yeah. Thank you.
Thanks for questions.
Did you find any relationship between the alphas and the deltas that you learned?
And you mean any relationships of the alpha and delta in the EMA layer?
Yes, yeah.
So we have tried that, but we did not see a clear interpretation of these parameters. So because the model is so large and so many parameters, we did not see a clear pattern how to interpret the learned parameters.
Do you spend any time considering how this might be applied to kind of continuous valued functions, things that like audio is kind of one obvious modality, but we've got a lot of folks who study EEG in the room, and that's kind of 256 channel brainwave recordings, places where you're looking at really long context kind of natively. Oh yeah, talk us through this.
Yes, that's a good question. So I think EMA is there is a great potential to apply EMA to the continuous signals, because EMA is from its own property, it's very good at modeling the local smoothing between local tokens, and I think this is a very good property fade the data like images or speech. So I think that's a very promising direction to apply our architecture to more advanced tasks in speech or images. Yeah.
What is the longest context you were able to sort of show good result?
So you mean empirical results, right?
Yeah.
So let's see here. So for our pre-training, we pre-trained on 32,000 tokens. And for evaluation, for example, if we just compute PPL, we see that even with 2 million tokens, our PPL still keep decreasing. So it means like it is able to stably model context length to 2 million tokens. And we did not scale it up because, you know, it is hard for us to find like meaningful context length longer than 2 million tokens, but at least till 2 million tokens, it's still working well. And for this long context QA tasks, for example, for narrative QA, the input is whole book, so its context length is around like 10,000, 200,000 tokens, or even longer. So we see that we achieve like good performance. It means like in some real tasks to like 200,000 tokens, it still works well. Yeah.
And do you see any like problem of forgetting in the middle and so on that people?
Yes, as I show in this figure,
Okay.
so we see that at some chunk boundaries, we still see the loss increases. So it means like there's still some like bottlenecks between the attention chunk boundaries. Even though like we see the final perplexity is good, but it means still like we see some like unbalanced distribution of the loss across different positions. So that's the one problem.
So in signal processing, people do things like overlap and add and so on. You know, just sliding window kind of.
Yes. So
Yeah.
I think that's maybe one direction that we can improve. Yeah.
And,
yes, thank you.
Nice. And what is the typical value of alpha? How many batches do you forget over, you know, before it becomes zero?
The alpha is a learn parameter. So
yeah, but I'm saying, what does it learn, kind of?
what
is the typical?
So as I said, like we try to display the alpha and try to interpret it, but we cannot find any clear pattern to show like how it's related with the data. And because alpha is always in the range from 0 to 1, so of course it is that it's a value, but we cannot say like why this value is better than other values. So we did not see like a clear pattern. Yeah.
Okay. Thank you. Very interesting.
Thank you.
Can you say anything about the geometry of the space that your X's live in?
The geometry of
like, do your X's live on any particular manifold, or do they have any randomly projected, learned? Yeah, what is that structure like?
You mean which part of the structure?
The input to the EMA layer.
Sorry, what's that?
Token embeddings?
Yeah, the token embeddings.
Oh,
So I'm talking about the token embeddings.
token embeddings.
Yes.
You mean sorry, I did not fully understand your question. So what is token embedding? So in pre-trained model, we just use BPE to tokenize the data, and we use like word embeddings, standard word embeddings for learnable word embeddings.
Max, thank you very much for taking the time to walk us through Megalodon. That was a really well-structured talk, and I think we learned a lot. It's very much appreciated.
Okay, thank you. Yeah, thank you, everyone. Yeah.
Cheers.